All right, well, good morning, everybody. I'd like to welcome you to one of our WIN seminars. Today we have the pleasure of having Professor Robert Scott give us a presentation on his work. Professor Scott's actually from Toronto, from what I understand, and therefore did his undergraduate work first at Western and then his master's and PhD work at U of T with Jeff Osen. Before going on to his postdoctoral work at Texas A&M with Richard Crooks, he then started in 2005 at the University of Saskatchewan as assistant professor in Saskatoon, and was promoted to associate professor in 2010. So his work is mostly related to nanoscale materials, especially in the catalysis area, and has a number of interests in that specific field, concerning fundamental aspects of catalysis, especially concerning bimetallic systems, oriented towards, of course, catalytic applications, green chemistry, applications in sensors for gases and other systems, light harvesting, batteries, and fuel cells, and as well he has a strong interest in characterizing this material, especially having access to the synchrotron source in Saskatchewan. He's published very consistently in high-quality journals over the years, mainly ACS-based journals, so this speaks for very high-quality work. And he will be speaking today, of course, about this general field of research, which is designing nanoparticles for catalytic applications. So please.
Yeah. Thanks very much for the nice introduction. And it's very nice to be here in Waterloo. I'm actually a Southern Ontario boy, so I actually grew up in Toronto and then lived in London a lot of my life. So Waterloo is right in between, and obviously passed through and been on campus quite a bit, particularly in my teenage years. I want to talk a lot about things that are going on in my lab at University of Waterloo, but first start with this idea of Saskatchewan. And every time I travel and you start talking about Saskatchewan, you start talking to people and you realize that this is the mental image that they have in their heads of where I'm coming from. And that this must be the chemistry department. And and to be fair, I meant this is certainly not the campus of the University of Saskatchewan, many mean, but certainly if you move out of the cities and the prairies, you certainly start to see scenes like this. It's not abnormal. But actually really interesting in Saskatoon, if you haven't been there, Saskatoon's actually a river city. So until you actually drive 10 minutes out of town, you don't even realize you're actually on the prairies when you're in Saskatoon. And so you actually have, as I say, 4 main bridges, the main downtown Saskatchewan, and then you can't quite see it, but the university is off to the corner there, right on the other side of the river from the downtown. Very nice, and there are actually miles and miles and miles of trails for biking and hiking all the way along the river on both sides of the river. So it's actually a beautiful place to come, particularly in the summer. What I want to point out is that I never been able to actually say this before, but actually came into Waterloo is actually, you can actually come to Saskatoon. It's actually warmer in Saskatoon right now than it is in Waterloo. And this may be the only time this is true in the next 10 years. But I actually left Saskatoon. It's actually a nice balmy 1 degree south. Every now and then in the winter you get the nice Chinooks coming in from the States, and Alberta, Saskatoon, and Saskatchewan get a little bit of a hiatus from the colder winter weather. Let's talk about a couple of things today. I want to talk about catalysis in ionic liquids, non-volatile solvents that are based on ionic salts, and particularly room temperature ionic liquids. And then the second half of the talk, I'm going to talk about polymer-stabilized bimetallic nanoparticle catalyst. And I'm going to talk about things that we can do at the Canadian Light Source in terms of doing chemistry while doing spectroscopy on the beamline, the Canadian Light Source. And the third major area of the group I'm not going to talk about today is the monolabor detected clusters of gold in particular, and trying to make catalysts from those systems. Now, this is a story. I have 2 kids now, and one of my kids, my daughter, really enjoyed this book when she was growing up. She's only 7 or 8 now. It's called The Dot, and I've read this about 100, 200 times when she was 3 or 4 years old. My son's starting to really like this book as well. And it was all about this young girl, didn't want to do any art, and the teacher said, you have to do something, try to draw something. And then so she said, fine, and she takes her pencil, she jabbed the piece of paper, and the teacher said, that's the nicest dot I've ever seen. And she said, well, that was really boring. And she thought about all the different types of dots you can make, different colored dots, hollow dots, the absence of dots, somewhere in the 40, 50, 60 readings of this book, I started to realize that this is what I do, is we make dots. And you talk about the idea of one-dimensional, two-dimensional, three-dimensional materials. When you talk about nanoparticles and clusters, you're effectively talking about zero-dimensional material, is making things down. And in the semiconductor community, of course, we actually call them dots. We call them quantum dots. The idea, of course, that properties of material change with size, and particularly the color, the absorption and emission of a given semiconductor, such as cadmium selenide, can change just by changing the size of the particles. And we have the idea then of plasmonic materials, and these are by no means a new technology, and it goes way back to Roman days in terms of gold particles, silver nanoparticles, actually absorbing light in the visible region. And of course, this is in the British Museum. The silver you're seeing there is actually bimetallic silver-gold nanoparticles that give you that silver color in the material. So they even figured out how to make bimetallic nanoparticles through way back when. Hollow nanoparticles, gold shells, trying to move absorption into the infrared. You have the porous material, the absence of dots, and of course the magnetic materials, and this idea of trying to make super paramagnetic material, taking ferromagnetic or ferrimagnetic materials and making them so small that they don't behave the same anymore, and then you get into your ferrofluids. Now, I'm going to talk about catalysis here, and this idea of using dots or nanoparticles for catalysis. This is not new. The petrochemical community in particular has been doing this for 50 years, but this idea of trying to use nanoparticles for heterogeneous catalysis for all kinds of different industrial reactions, hydrogenations, oxidation, carbon-carbon coupling, and particularly in Alberta, cracking oils into smaller hydrocarbons. And you think about what you want to do in terms of making, using nanoparticles. You really want the high surface area. You want a minimal amount of precious metals. And you generally want them in porous supports at fairly low loadings. And you look at the most commonly used metal catalysts, you see right away palladium, platinum, ruthenium, rhodium are on that list. It's a very expensive catalyst, and so you don't want to be wasting these materials by any means of the imagination. And so if you look at think about nanoparticles themselves, and by the time you've got to something that's a 2 or 3 nanometer nanoparticle, you've already got a situation where you've got 5 shells of effectively atoms built up, and only about 45% of the atoms are actually on the surface of that particle. Right? So effectively, you're wasting half of your material by the time you've even made a 2 nanometer particle is wasted in terms of catalysis. Right? It's not going to be accessed at the surface, not going to be able to. So there's been a movement in the catalyst industry, certainly, to try to make smaller and smaller clusters. And the idea you can get all the way down to something, for example, a 13-atom cluster that would have 92%, 12 of the 13 atoms on the surface available for catalysis, wasting very little material. Right? This is obviously a challenge. I'm going to talk about, as I go through, this idea of how can we make particles smaller, and talk a little bit about other strategies we can do to make have better atom economy for catalysts. Okay. Let's switch then to this idea of ionic liquids, and we moved into this when we first started in Saskatchewan in 2005. There were reports of this idea of people being able to make metal nanoparticles for catalysts, and they called them so-called naked nanoparticle surface in ionic liquids. And they're kind of curious about these types of systems. You have non-volatile solvents, the possibility of stabilizing nanoparticle catalyst, and the idea you could bring a substrate in, do a reaction, pump the substrate off or boil the substrate off, but then you can continuously reuse potentially the catalyst system. And there's all kinds of ionic liquids out there. I'm going to talk about a couple in particular, and that is the imidazolium system as the cation. methylbutyl imidazole, imidazolium cations in particular, and I'll talk about tetraalkylphosphonium cations as well. But there's all kinds of possible permutations and different cations and different anions that you can use. And there's a lot of people who've been playing with ionic liquids for catalysis. In the biofuel industry, this idea that imidazolium ionic liquids in particular show very good solvents for cellulose solubility. So we can actually dissolve cellulose and break down cellulose in ionic liquids at essentially room temperature conditions. The idea of reusing nanoparticle catalyst in ionic liquid, bringing in a substrate, taking out a product, and just keep reusing that system. Taking phenols, for example, that might come from lignin, and being able to hydrogenate phenols and hydrodeoxygenation routes to make hydrocarbon. And there's also been a huge amount of work in terms of carbon dioxide capture, and particularly using anions that will react very, very readily with carbon dioxide, such that your ionic liquid is still a liquid, absorbs carbon dioxide in a 1-to-1 ratio with the anion, and then release it again later on. So all kinds of wonderful things that people have been trying to do with ionic liquid. The biggest problems that you come with the ionic liquid, though, is that this is a really expensive solvent system. And so if you're suddenly taking something, going away from water and organic solvent to a solvent that you have to make and design and synthesize, you better be able to reuse it over and over and over in catalysis. There's all kinds of interesting properties. High polarity, very negligible vapor pressure. That negligible vapor pressure is a double-edged sword because it also means you can't purify it as you do most solvent. Right? We normally think about solvent stills and purifying solvent by distillation. That's not possible for many ionic liquids. But there's this idea then that these are essentially, if you will, many of them are surfactant solutions really. But you get very low interfacial tensions, very high viscosities for some ionic liquids that may help stabilize nanoparticles. And people are trying to understand how a nanoparticle gets stabilized in these systems, particularly when you use weak anions, and also worry about the fact of possible impurities. Right? Because you can't easily distill an ionic liquid, you have to worry about how you made it and what impurities might be there. So we got going on this system almost 9 years ago now, and it very quickly realized that in order to really study these systems well, we had to make them ourselves. Here's a not particularly difficult synthesis, but industrially you don't typically get nice, clean, clear ionic liquids like this. The imidazole in air easily oxidizes. You get very colored impurities that are very hard to work with and very hard to separate from the ionic liquids once they're made. So most of the synthesis is actually done under nitrogen. Distill all of your precursors under nitrogen. Very mild reaction in toluene, methylimidazole chlorobutane, for example. You get your chloride salt, and then do an ion exchange with the chloride salt to get your hexafluorophosphate salt. In order to make really clean ionic liquids, at which we can't even detect any possible impurities, including the starting material methylimidazole, we actually have to do 3 or 4 recrystallizations of our intermediate precursor here. And so in terms of a sustainable green solvent, I mean, this is a very, very labor-intensive, wasteful process to make the solvent. Right? So we better be using this over and over again once we make it. Then we get into this idea of trying to make nanoparticles in these systems. And we had 2 routes to doing this. One of them is the little bit more boring route. Let's take nanoparticles in other solvents and then phase transfer them over to the ionic liquids. So for example, we can take polyvinylpyrrolidone, polymer-stabilized particles, in things like methanol. Very easy synthesis. You can make these things very easily, put them into the ionic liquid, and then pump off the methanol. Right? The idea of the ionic liquid is non-volatile, doesn't go anywhere, and this works really well. Of course, you have the polymer in there as well, so maybe not quite as intricately beautiful, but nevertheless, we do get no minimal change in the particle size upon transfer of particles from one solvent to another. And we can do this for things like palladium, which is a very well-known catalyst. We can do things like gold, and you can see that we get very, very small changes in the plasmon band of gold particles as we transition the methanol to the ionic liquid. We weren't so interested in this route because we wanted to get away from using polymer-stabilized systems to begin with. We wanted to go toward direct synthesis. I want the ionic liquid to be the stabilizer as well as the solvent. And this is problematic, and there was all kinds of literature that was contradictory in this when we first got in here. We had issue trying to make stable systems, and we found that over time, you make gold nanoparticles, you get a nice, beautiful red solution. You come back the next day, and you've got to precipitate in the bottom of your flask. So they weren't doing very well at dispersing the gold systems, even though others had noticed this. There were routes around that. Audrey Morse, for example, McGill is one person who's doing that. And that is to bring in functional groups, for example, thiols, on the cation of the ionic liquid, and then that would lead to even further stabilization of colloids. That's doable, but then that creates another synthesis step in your ionic liquid, makes it that much harder to synthesize and purify. So we want to stay away from that. We try to understand what was going on. And it turned out, for making gold nanoparticles, the starting purity of the ionic liquids we made was the critical parameter in how stable colloids were in that system. And here's the idea then of a as synthesized in ultra pure ionic liquids, very low halide levels, very low water levels, and we've essentially taken methanimidazole levels down to below the detection limit by NMR. And we make them, and then over time, you can see a little bit of precipitation over time in 7 days. The particles slowly start to precipitate out, and you look at the electron microscopy image over time, and you see the larger aggregates of particles that are precipitating out. If you go in, though, and you add in the methylmidazole starting material at very, very low levels, 1 millimole, barely detectable by NMR, all of a sudden, you get magical stability again. And so it turns out that what was the discrepancy in the literature was the fact that some people had a little bit of starting material impurity, very difficult to remove once it was there. Adding that little bit, you get perfect stability over weeks and even months. Very reproducible plasmon bands over time, and much more well-dispersed particles in these systems. And so it turns out more and more we did this system, we realized that what the critical parameter in most of the imidazolium ionic liquid was for nanoparticle stability was the methylmidazole impurity. Right? And so if you pull them back in there, that certainly helps you with stabilizing particles. And at the levels we're making particles in the micromole concentrations, you're still talking about, even at millimole levels of methylmidazole, 30 to 40 methylmidazole molecules per nanoparticle that are available in that ionic liquid. So there's even at low levels of impurity, there's still a substantial amount of impurity to stabilize nanoparticle surfaces. And this came out true as well for catalysts. And the idea of an unstabilized system, and this is actually a palladium-gold bimetallic mixture, so we took palladium salts and gold salt and reduced them together. If we had no further stabilizer beyond the ionic liquid, we see the hydrogenation activity drop off very quickly, and you can actually start to see the precipitate of the particles, the aggregation of the particles in the system. You add the methylmidazole impurities back in, stabilizer impurities, if you will, back in, much better stability. Or if you come in with polymer-stabilized particles to begin with, you get much more stable catalyst that you can use and reuse for multiple catalytic cycles. Okay. So we started to figure that system out, but that was a little upsetting to us because the ionic liquid itself wasn't really stabilizing the particles. There was really an impurity in the ionic liquid. So we switched to another system. And this is actually a system that's actually made in Canada, which is the tetraaquaphosphonium systems. Niagara Falls, this is one of the last few factories in Niagara Falls. Cytec Canada has a factory just outside Niagara Falls. They're one of the world's largest phosphine plants. And one of the other things they're making in that plant is the tetraaquaphosphonium salt as well. Okay? And if you choose the right alkyl groups and particularly you have one long group and three shorter groups on these particular systems. A lot of the tetraalkyl phosphonium halides are in fact room temperature ionic liquids. So this was a really interesting system. So we started with this. The system we started with was a 66614. So 3 hexyl groups and a C14 group on every phosphonium center. Add the gold chloride salt, add lithium borohydride as reducing agents to get the gold nanoparticles in the ionic liquid. These same particles, and this is a very large batch that we made right at the beginning. We usually make much smaller batches than this. But the first particles we made over 3 years ago are still sitting in our lab, well dispersed. A very, very, very good system for stabilizing nanoparticles, much better than the imidazolium system. Particles do oxidize in this system if you leave them in air. You have very strong halide environments. Think about halide effects on metal redox properties. But we can regenerate oxidized particles by re-adding lithium borohydride. I'll talk about an advantage of actually oxidizing particles in a second. And so this is an interesting system. We tried to understand why this was, and we played with a whole bunch of different anions. It turned out the halides are the best. And you think about the halides actually absorb very, very strongly to metal surfaces, chloride, bromide in particular. Iodide it does as well, but then you have some iodide-iodine chemistry that you would like to avoid. But essentially a halide absorption, a co-absorption of the cation with that halide. And this is so-called electrosteric stabilization, that you have a electrostatic stabilizer, if you will, in terms of a negatively charged chloride, but then you've got the steric bulk of the cation that are also there. If you actually think about this, this is very similar to a lot of things you see in nanoparticle literature for the tetraalkyl ammonium groups. So tetraalkyl ammonium bromide, cetyl-trimethyl ammonium bromide, very common surfactants for stabilizing nanoparticles. Here's a phosphonium system that's effectively acting as a surfactant and a solvent for nanoparticle stabilization. The really key thing I want to point out here is that even though you do have the stabilization, you're not poisoning these surfaces. And a lot of people, particularly in the engineering community, really like to avoid halides because they're worried about halide absorption and therefore poisoning of metal surfaces. Point out you can do a lot of catalytic reactions, fairly good yields in these ionic liquids. So as an example, we started out looking at hydrogenations of all different types, all the very, very simple hydrogenations to looking at possible selective hydrogenations. And all the way through, you get very, very strong hydrogenation catalyst. This is with palladium nanoparticles, by the way, sorry, in the ionic liquids. And we're seeing very, very strong hydrogenation. And depending on the conditions, you can sometimes get selectivity, for example, in the diene to the monoenes that I have there. But that's mostly just on the catalytic conditions themselves, what temperatures and how long you actually do the catalytic reactions at. Be able to recycle these systems really, really well because these are non-volatile liquids. Very easy to pump off the products at the end of the reaction. The catalyst stays behind in the ionic liquid. And so we've been able to do the same reaction over and over again over time. And in the case of palladium nanoparticles for this particular allylic alcohol hydrogenation, we do see over time that the particle size goes from about 2.5 nanometers to about 5.5 nanometers after 5 cycles. So there is a little bit of sintering going on with nanoparticles. They're getting a little bit larger as we do more and more catalysis. And this is one of the things that we really worked on, is that obviously this is a drawback, is that our surface area, if you will, of effective metal on this, is dropping over time. We found that now we can oxidize the palladium in air and then reproduce it to bring back the activity of the catalyst. And this is something we've spent the last couple of years really focusing on, this idea of re-dispersion of catalyst in ionic liquid. So we start with a catalyst, we've run it for 5 cycles, it's gone to about 5.5 nanometers, the activity has started to drop off because the size is getting larger. but we're in a halide ionic liquid, right? We have a huge concentration of halides in there. All you need to do is open up that, heat this in air, 80 degrees Celsius. After an hour or so, you've got complete oxidation of the palladium back to the palladium chloride salt. Re-add a very small amount of the initial reducing agent. We've got back to a palladium nanoparticle system, but we got back to smaller particle sizes than we originally started with. Right? And so this idea that we've got a system now that we can potentially keep reusing over and over again, and then anytime the activity starts to die on us, we've got a possible, very simple route, one-part route that essentially involves oxidizing in air and re-reducing to form smaller particles. So that was the system for palladium. We tested this with gold. Most people don't think of the idea that gold can be oxidized, but in the presence of bromides and chlorides in particular, there is mining literature that this is a possible way to oxidize gold. It actually takes upwards in the air 2 to 3 days to completely oxidize gold particles to their salts. We can cheat a little bit by using things like hydrogen peroxide, in which case this takes minutes. And so add a little bit of hydrogen peroxide, we can very easily take the gold, it re-oxidize it to the gold chloride, and then we can re-reduce it with lithium borohydride to smaller particles. So this is a particular picture of particles which we sintered, a much larger particle size, closer to 10 nanometers. We've re-oxidized them, we add the reducing agent, we're down to a system that now has a particle size of about 3 nanometers. Right, so, and I like the gold because the gold has the nice plasmonic color that changes with size, so you can visually see what's going on just by the UV vis alone. This is really all interesting. There's other people in the heterogeneous area working on re-dispersion of catalysts. Many of them involve heterogeneous catalysts. For example, gold nanoparticle catalyst, Hutchings, for example, has shown that you can bring in methyl bromide, methyl iodide, and essentially redisperse gold particles and then basically cut down particles into smaller and smaller particles over time. And this is another strategy, except we're not a true heterogeneous system. It's a solid and a liquid system, a so-called quasi-heterogeneous system, but a very, very readily redispersed. So we wanted to continue to play with this redispersion and see how general it was. So I challenged the students in my lab to say, go through all the possible catalytic transition metals and see how many of them can you redisperse in the ionic liquids. And the answer is pretty much all of them. The only system we have a little bit of trouble with is iron. X-ray absorption studies show that the iron nanoparticles actually aren't pure iron nanoparticles, they're a little bit oxidized. You have trouble completely reducing the iron. But nevertheless, in all the other systems, it's very easy to make particles with any kind of reducing agent. Some of the 3D transition metals, you need to do stronger reducing agents, such as lithium aluminum hydride. And then the idea of bringing oxygen and or peroxides in to re-oxidize them back to their chloride or bromide salts and back and forth again. And point out the things we know about, for example, the silver chloride chemistry that we have to worry about in water. We don't have to worry about silver chloride precipitates in the ionic liquid, completely different solvent media. You get silver 1 chloride salts that are quite soluble in these ionic liquids. So we've gone through a large amount of different types of catalysts, shown redispersions of different types of catalysts. We've spent a lot of time on silver, gold, a little bit on copper, and nowadays we're spending a lot of time on iron and trying to find ways of doing iron a little better. And one of the problems you have in this system is that you notice that lithium borohydride, lithium aluminum hydride are a little bit stronger reducing agents than one would like to use in these processes. This is the effect of using halide media, right? Metals oxidize much easier in halide media. You need much stronger reducing agents to re-reduce those metals in that same media. So this is one of the problems, is that you can't actually use things like hydrogen gas, which is what we wanted to, very easily in these ionic liquids. Most of these metals actually won't reduce under hydrogen gas in these halide media. They certainly will in water, but in these particular solvents, they will not. So we continue to play with this system. It's a very interesting system. We've got some recent work on hydrodeoxygenation of phenols in these same ionic liquids. That's actually a very recent article in Green Chemistry, advanced article right now. We're also continuing to play with that idea of the gold oxidation. You got to, particularly in the bromide ionic liquids, the rates at which gold oxidizes in these bromide ionic liquids actually gets very close to what you would see if you use cyanide as the oxidation promoter. And that means that there's a possibility of trying to get away from messy, dangerous cyanide chemistry into chemistry that might be a little bit more environmentally friendly. The other thing we're continuing to play with is carbon dioxide reactivity. A lot of people have been playing with this idea of absorbing carbon dioxide in ionic liquids. We're trying to take it one step further and actually react that carbon dioxide once it's in the ionic liquid. So the idea of an activation step and then a reactivity of that activated carbon dioxide instead of just trying to desorb it again. Yes. The other thing is switch gears a little bit and talk about bimetallic particles. And we've been playing with a couple of different systems in the last few years in bimetallic. And I'm going to talk about one in particular, and I'm going to put a lot of emphasis on the palladium gold system. This is a very, very promising bimetallic system that's been developed in the last 10 to 15 years. And most of the advantages take advantage of the fact that the electronegativity difference between palladium and gold, very slight, but gold is generally slightly more electronegative than palladium. And I'll get back to this and how this affects catalyst as we move through that story. The other thing we've been playing with a little bit is trying to maximize atom economy. And so I talked about at the beginning this idea of making smaller and smaller and smaller clusters to get more of the expensive metals on the surface. Your alternate route there is to put a monolayer of a second metal on a cheaper core, right? And then if I can keep that monolayer of a second metal on the cheaper core, the idea that I can thereby maximize the catalytic activity of that metal by having most of it on the surface. And so I have an example here of a palladium core, shell on silver that we played with. These are tricky systems because this system in particular is a wonderful hydrogenation catalyst, but you open up to air and the silver starts to oxidize and it actually starts to invert itself in structure. And so there's a lot of issues in making things like this and keeping them that way. The bimetallics have been all over the place in the last little while. In particular, Eichhorn's group has been doing a lot of work with platinum ruthenium nanoparticles, fuel cells, for preferential carbon monoxide oxidation in the presence of hydrogen, trying to remove carbon monoxide impurities in hydrogen gas. Palladium platinum nanoparticles for hydrogenations have been looked at by a number of groups. And the palladium gold system in particular has been looked at by a lot of groups, in particular Graham Hutchins' group. All kinds of different reactions, and particularly the one that's really attracted is hydrocarbon oxidations, alcohol oxidation, and now a direct hydrogen peroxide synthesis from hydrogen and oxygen gas. You actually go to your inorganic textbooks and you look up hydrogen peroxide synthesis. A lot of them actually say it's impossible to make hydrogen peroxide directly from hydrogen gas and oxygen gas. That's actually no longer true. There are commercial processes now being developed using palladium gold catalyst. The issue when you start getting to bimetallics is now you've got two metals in the same particle. You've got a huge number of possible structures possible. And versus the alloy core shell types, I call cluster and cluster systems, which you have particles growing on other particles. Subsurface shells, which have been shown in a lot of single crystal studies, have been very important. And then intermetallic compounds that can be formed. And so not only trying to synthesize these things, but actually characterizing specific structures and trying to keep them that way during catalysis. So we got into this field when we first started in Saskatchewan. The first thing we started to do was we saw a paper in 2005, Japanese group, and they were using polymer-stabilized gold particles for the oxidation of alcohols to aldehydes and a little bit of benzoic acid and its ester. This was in water, so solution chemistry, a little bit of base there, and polyvinyl pyrrolidone again used as the polymer stabilizer. And we had some previous experience in palladium-gold systems. This is a system in which gold actually had higher selectivity to the aldehyde than, higher activity to the aldehyde and acid than pure palladium did. But palladium systems actually had better selectivity to the aldehyde. So we started playing with bimetallics for this system. We tried a couple of different ways to make bimetallic nanoparticles. First one is to take both salts, add the reducing agent in the presence of both salts. Both gold chloride and palladium chloride salts reduce almost instantaneously in water with sodium borohydride. And so because both have very fast reduction kinetic, this is potentially a way of making alloy particles. I say potentially because, and we've done a lot of characterization to find the particles you do get are actually very close to being alloys. I'll talk about how we do that. The second method is to pre-synthesize gold particles and then do a secondary growth of a shell on those particles, and that is usually involved bringing in a weaker reducing agent such as ascorbic acid, and in control conditions we can get essentially the gold nanoparticle is catalyzing the growth of the palladium onto its surface. And you really want to avoid the idea of any possible secondary nucleation of pure palladium particles. That is, we want to grow from the gold. We don't want to form new particles with pure palladium. So we started with the co-reduction. And it turns out we can get wonderful catalytic activities for alcohol oxidation. This is at just over 60 degrees Celsius in water, 1 atmosphere oxygen, all the way from benzoyl alcohol, primary alcohol, secondary alcohols, allylic alcohols, diols. All of them are reacting. Diols are very interesting to get pure selectivity to the lactone. And we started to see in a lot of these systems is that you get fairly good selectivities to the aldehyde in short periods of time, and then over longer periods of time you get more and more acid buildup. So the idea that you form the aldehyde and then the aldehyde further oxidizes to the acid. One reaction kept standing out, and that was the allylic alcohols. In that we started out with very poor selectivity towards the aldehyde, in this case the quinaldehyde from the proto-alcohol. But then over time it got more and more and more selective to that aldehyde. This is very unusual in a catalytic system that your selectivity gets better and better and better as you're going on. And it seems to suggest that something was changing in our catalyst as the reaction was proceeding. So we continued to investigate this system and try to understand how these allylic alcohols are reacting with palladium gold particles such that we're getting better selectivities over time. And it turns out there's a lot of literature on people playing with allylic alcohols with palladium, and it turns out palladium-2 salts actually react with allylic alcohol stoichiometrically. 1-to-1 reaction, you get the aldehyde, you get palladium 0, this usually gives you palladium black. Mark Lawton in Toronto actually did his PhD on this stuff way back when, so this is old chemistry. And so stoichiometric reaction, not a catalytic reaction, and in fact that's what we see by just using the pure palladium salts, we get stoichiometric reaction. But suddenly, if we mix gold particles and palladium salts together, we suddenly start to get very active catalyst. And the idea being is that you're making palladium 0 in the first step of a palladium salt reacting with our allylic alcohol. But the idea, if you have gold particles around, there's a nucleation center available for that palladium to nucleate onto. And so essentially, we're making core shell particles, if you will, of palladium reducing onto the gold. And so we wanted to test that as we started to get very good catalysts. It said, well, if that's the case, then if I start by making a core shell catalyst through my sequential method, I should get a better catalyst. And so they use the ascorbic acid method, make the core shell catalyst. And in fact, these are the best catalysts we've had to date. Gold cores with palladium shells, 80% conversions, 90% selectivity to the aldehyde. Very, very, very strong catalyst. In terms of the actual structure, and I'm going to talk about XFs and things in a second, it turns out that there's a little bit of still surface gold in these systems, and so we think it's closer to the cluster and cluster structure, that it's not a true palladium shell, but it's more palladium nucleation onto gold particles. kept trying to understand the mechanism of this and realized there's two possible mechanisms here. One of them would be a redox mechanism. We know palladium-2 salts react stoichiometrically with protoalcohol. So we have the idea then that potentially if the palladium could reoxidize, then, for example, in the presence of a halide, we could then have a redox cycle in which the palladium is essentially going from the particle back into solution over and over again. Or we could have a system in which the final material, once we have the palladium reduced onto the gold, is in fact the catalyst, and we have the alcohol come in, beta hydride abstraction, and then essentially the only role of an oxygen in such a mechanism is to essentially clean up the surface hydrides off the system to form water. There was a little bit of evidence for this mechanism in our products. We see a lot of isomerization and hydrogenation products early in the reaction, a little bit anyway, sorry. And that seems to suggest that there may be some hydrides around early in the reaction in particular, which may lead you to that second mechanism. So we started getting into more and more on the Canadian light source and trying to understand absorption spectroscopy and about what that could tell us about the catalytic mechanism that we had here. And so very, very quick primer on X-ray absorption spectroscopy. This is the edge, the absorption edge of a given element. We have our near edge spectroscopy, which would be atomic transitions very close to the edge, followed by the oscillations that we know as extended X-ray absorption fine structure, or XAFs. And this tells us a lot about the coordination environment because the photoelectron is escaping and scattering off nearest neighbors up from the absorbing atom. So it tells us how many nearest neighbor an absorbing atom has and what they are. And it turns out the frequency of this oscillation had to do with bond distances, how close the scatterers are, and the amplitude of this oscillation had to do with electron density, therefore what that scatterer is. So we got two major experiments that we can do with the CLS on these systems. Gold is one. The L edge, for example, in gold, 2p to 5d transitions at the edge. Most of the gold particles have D10 environments, in which case the spectroscopy at the edge is not particularly informative. But we can also look at the palladium, and this is where things get a lot more interesting. We can look at either the K edge of palladium, which is the 1s to effectively 5p transition, or we can look at lower energy, which is the L edges, which are the 2p to 4d transition. Those are really interesting because they probe the 4d occupancy of the palladium, and so we're talking about different palladium oxidation states, palladium-2 versus palladium-0. We'll see a difference in the intensity of the transition at the edge, depending on what the oxidation state of the palladium is. And we actually want to go one step further. Instead of actually just making the catalyst and then removing them from the system, trying to keep them away from air and finally get them on the beamline, I want to do all the chemistry on the beamline. And so this took a couple of years to develop, including time I was on sabbatical, but we now have solution cells. We can actually do the spectroscopy while we're doing the chemistry. And so, for example, this is a solution cell. There's a 5-micron polycarbonate membrane on the surface of that. There's a little stir barrel in there is being addressed. And so this solution cell is sitting right in the middle of this aluminum box at a 45-degree angle from the X-rays coming in. And there's a fluorescence detector over here and a transmission ion chamber over here. High energies, we can do transmission experiment. Low energy experiments, we can do the fluorescence experiments. Now we can do things under the real conditions, try to understand the electronic properties of these catalysts. Some of the issues, we do have to come in with higher concentrations than we normally do with catalysis. We really have to watch out with beam damage. You're coming in with very, very high energy X-rays and a very high flux of X-rays. And X-ray absorption spectroscopy gives you average information of all of the metals in there. Generally, you want to have smaller particles if you want to get surface-specific information. So the idea then, this is our first foray into the realm of in situ measurement. The palladium K edge, and so the experiment is that I have my polymer-stabilized gold particles in water. I've added my palladium salt, time 0, I'm adding my proto-alcohol to get this thing going. This is actually done at the, in Chicago at the Advanced Photon Source. We can now do this at the Canadian Light Source as well. And effectively, is at time 0, we add the proto-alcohol, we start monitoring the reaction. And so here at the spectroscopy, the palladium K edge, 1s to 5p transition effectively at the edge. A little bit boring at the edge, but you do see small features at the edge that are changing. And you can actually, if you come in with standards on palladium 0 particles and palladium chloride salts, you can actually fit the Zane linear combination fitting, and we can actually pull out from these spectra how much palladium 0 there is as a function of time. You can actually follow the kinetics of the palladium reduction in real time. And this is a really, really a difficult experiment to do by any other technique. Things like XPS, you generally ultra-high vacuum conditions. We can't really readily follow oxidation states in solution. You also, from the oscillations in the X-shafts through the Fourier transform, you get something that's very similar to a radial distribution function. It's a phase-shifted radial distribution function, essentially. But you can see, essentially, that the palladium chloride band is dropping down. A palladium gold band is rising. And again, really good support for the idea that the palladium chloride is being reduced onto the surface right at the beginning of this reaction when we start with palladium salts. We want to go one step further then and say, okay, what happens if we now bring air into the system? And we wanted to look at the L edge, which is to be a little bit more informative of what's going on. Lower energy edge, 2p to 4d transition. The palladium salt before reaction, very strong white line intensity. You have a D8 system, 4d8 system. There are vacancies in the 4d orbital, therefore a very strong transition. And as soon as you add the proto-alcohol, the very next spectra, the red one there, you see a loss of the intensity because you've filled the 4d orbital by reducing the palladium in the system. What's interesting is that 3rd, 4th, 5th, 6th GANs all look exactly the same as that red one. It never actually approaches pure palladium metal. That is, it's always slightly higher in intensity and slightly shifted in energy compared to the pure palladium metal. This is evidence of a little bit of a 4D deficiency in palladium on the gold. And the idea, again, that gold is a little bit more electronegative than palladium, so gold is pulling a little bit of 4D electron density away from the palladium on the surface, and that's leading to a little bit of a spectral shift in the system. Then what we did is that you have one-to-one equivalent in proto-alcohol allows the complete reduction of all the palladium. And then we said, well, what happens if we bring oxygen back in? Can we re-oxidize the palladium again? 7 hours later, this is the red spectra, zoomed in on the red spectra. 7 hours later, exactly the same spectra. Once the palladium has been deposited onto the gold, it does not get re-oxidized by oxygen again. And this is actually much better than the stability of pure palladium, which does get oxidized under these exact same conditions. So the idea that this turns out to be a really interesting catalyst, likely because the gold is stabilizing the palladium to oxidation. And so you think of an oxidation catalyst, one of the first priorities of any oxidation catalyst is it should be stable to oxidation itself. And the idea then in the palladium-gold combination is that the gold seems to stabilize the palladium to further oxidation because it's already withdrawing some electron density from palladium. It's making it harder to further oxidize. Continue to work with this, and I know I'm running out of time, but just show you all kinds of other things we can do. Now that we have that liquid cell, we said, well, let's think of things we can do. First one we thought of is iron. And we said, well, can we watch iron particles rusting in solution? And time 0 would be that we add air to the system and see, can we spectroscopically see what happens? This is just for fun, if you will, but there's also a lot of really interesting science questions in terms of iron oxidation. And in fact, you can follow the spectroscopy changes, iron oxidizing to iron 2, iron 3 over time. And you can actually see in the TEM, you actually get iron particles and you get the oxide layer around and the central iron particle in the center of every particle. We also have these have been used by a lot of groups of really interesting catalyst supports because you can bring other metals into the system and somehow the iron in the core can react with other metals in a galvanic reaction to deposit the second metal on the surface of the particle, even though spatially they should be separated by that oxide layer. And so we tried to follow that up and look at palladium coming into the system, And sure enough, we take those iron oxide particles, the palladium LH spectra, time 0, we have a 4D8 system. Within 5 minutes, that palladium is fully reduced on the surface of the iron oxide particles as palladium 0. And XSAFT actually shows that these are actually palladium clusters of about 1 to 1.5 nanometers in diameter. All kinds of things going on at the light source. The Canadian light source now just hit its 10-year anniversary. There's a big user meeting coming up with a lot of a major material symposium in May. One of the big things that have been going on in the light source is now that a lot of the beamlines are up and running, there's still more beamlines coming. A lot of people have been pushing towards in situ, doing more interesting measurements on the line. I talked about the liquid cells we developed. We have a gas cell that allows you to put six samples into a 6-shooter such as this. You actually put a furnace over there so you can do transmission measurement. And we're also developing a gas cell that will allow you to do measurements of heterogeneous catalysts using fluorescence measurements. That's a little harder because then you have to have microheaters instead of furnaces over the whole quartz tube. Ian Burgess' lab has been doing a lot on spectral electron microscopy on the mid-IR beamline. And Derek Peake in soil science in the University of Saskatchewan has been collaborating with Tom Regier, who runs the HRTEM beamline, lower energy beamline. They actually have a liquid cell that allows you to probe 3D ledges. So now you're talking about your 3D elements. And this is actually a liquid cell that's under ultra-high vacuum. It has a 250 nanometer silicon nitride window, and you actually bring in the solutions through HPLC tubing on the back end. So really, really interesting things that you can do with these types of measurements. Okay. So just to take-home measurements, and I showed you a few things today. This idea of the ionic liquids are very attractive solvents. And I really want to point out, these are extremely expensive solvents, so if we're ever going to do anything with ionic liquids for real catalytic application, you have to recycle and reuse over and over and over again. Re-dispersion strategy is a step in that direction, but I'll point out we kept adding more borohydrides into the system. We haven't found a way to avoid that yet, but it's certainly going to lead to a buildup of borohydrides and borates over the reaction. Talked a little bit about the X-ray absorption measurements for palladium gold catalyst, and this idea that very resistant to oxidation once palladium is on gold. And then finally, the take-home message is that there are many beamlines now, the hard energy beamline, tender and soft energy beamlines at the CLS all have liquid cells available for in situ work. Gas phase work in heterogeneous catalyst. We have a transmission cell for the 4D, 5D edges. There is still more work being done on SGM to allow for potential ambient atmosphere conditions in that line as well. Finally, acknowledge the people who actually did the work, and there's been a huge number of people on these projects over the years, and particularly Ronnie Banerjee in my lab is just finishing up, done all the tetraalkylphosphonium work and the re-dispersion along with Robin Theron. SciTech has supported us by giving us many ionic liquids for this project. And on the bimetallics in particular, I want to point out Amy McClellan. She did all the initial in situ measurements. She's actually now one of the beamline scientists, associates on the XSRB beamline. So she, as I say, the expertise is there for other people to do it. A lot of different collaborators, particularly the Canadian light source Yongfeng Hu, who runs the XSRB beamline, and many collaborators on campus at the University of Saskatchewan. I just point out at the University of Saskatchewan, there's a lot of interesting things going on. There's a major solar photovoltaic group now formed. Tim Kelly, who's a research chair in photovoltaics, came on board about 4 years ago. He's been doing a lot of really interesting work, including recent work on perovskites, and a huge collaboration that started with Ron Steer on looking at upconversion. So trying to take very low energy light and upconverting it for use in photovoltaics. So there's a lot of materials work going on at University of Saskatchewan over the last 5 years. More than anything, please, thanks very much for coming out this morning, and I'll be glad to answer any questions you may have.